Why, hello there, children. All right, so let's continue along our derivative path. Let's find one more derivative similar to last night's homework. Hopefully you checked your answers with my worked out work on line. But set this one up again, find the derivative using our limit definition. So pause the video, set it up, and then check to see, does your work look like mine? Again, so a question very similar to last time. We have our derivative of our original function, and no need to multiply it down there. All right, so at the end of last time, during class we saw questions very similar to those. Here are the original functions, and here are the derivatives. And everyone was like, "Oh, there's got to be a pattern," and there was just thirst for more math knowledge. And so we said our pattern was the following: if we have some polynomial, x, say, raised to the n power, well, to find the derivative, we're multiplying by that exponent out in front, and we're subtracting 1 from the exponent. And if there was a constant there, sort of like here, 3x squared, you multiply by the 2, and you get 6, and you drop the exponent by 1. So same rule, just you happen to multiply the constant that's out there. One thing we might not have said is if f of x equals a constant, so maybe like f of x equals 5. Well, what is that on a graph? If you graph f of x equals 5, it looks like a horizontal line through 5. What's the slope of any horizontal line? 0. So we maybe didn't talk about that, but I think that makes sense. If you graph it, hey, the slope is 0 every point on any horizontal line. So that's why the derivative of c, we're saying is any constant, equals 0. These ones the book also writes out. It's just saying that you can find the derivative of polynomial altogether and just do each piece separately. So what I mean by that is if you look at something we've done, like this question. One way you could do it is just take the derivative of 2x squared and then just do 4x using limit definition, and then just do 2, or you can do them all at the same time. And that's the way we've been doing things. We've put them all together into our limit definition and found them. But you could do it either way. So today, let's use this shortcut. Take a minute and do example 1. Find the derivative for each of these functions, not doing the limit definition. Now we're just going to use our shortcut. And this here, since these are powers, we're calling this our power rule. This is our power rule. We can just, well, you try it and see if you get the same thing as me. Right, we're multiplying by the exponent and dropping it by 1. Constants go away, right? Really, do they go away? What are we saying by they go away? Well, the slope of a constant of any horizontal line we said is 0, so we don't need to write plus 0. And again, b is the same thing. Multiply, drop the exponent by 1. Multiply, drop the exponent by 1. Please make sure you're writing the proper notation, because if you start getting sloppy and you don't write what is 5x to the fourth, we're not going to know whether it's the derivative or the original function, and eventually we'll have second and third derivatives. So again, notation is important. All right, pause the video and try these ones. These require a little more of our algebra skills. Notice our rules. Notice our rules. X, the variable, is in the numerator. So you can't use our power rule until you have x raised to a power. So rewrite the square root of x as something raised to a fractional power. And rewrite x we can't have in the denominator. Again, our rules are only when we're talking about numbers in the variables in the numerator. So rewrite that first, and then you're able to find the derivative using our power rule. So again, be careful with those algebra rules. I multiply by a half here, and then I subtract 1 is negative a half. I'm also, usually our book and directions, excuse me, will tell you don't leave any negative exponents. So I can make x a negative 1/2 positive by throwing in the denominator. Same over here. I multiply by negative 1 out in front. I subtract it. You get negative 2, but don't leave that out in front. Throw that in your denominator. And I did the same thing with d as well. So now the question adds a little piece. It says find the slope of each curve at the given point P. So here's some function, and I want to find the slope at negative 1 comma a half. Well, who knows where negative 1 excuse me, comma a half is? Somewhere over there. We want to find the slope of the line that just touches that one point, right? Of the tangent line right at that point. All right, I want to find the slope of a curve. That's exactly what we've been doing in all these questions, right? The derivative is the equation for slope at any point. So your first step, we'll do the first one together, find the equation for the slope of this function. Right, so I multiplied by 4. I got 4 over 2 is 2, and I dropped my exponent by 1. So I get 2x to the third. Oops, I'm writing in red. So that is the equation for slope at any point, but we want just the slope at this point that they told us. So all we're going to do is, hey, plug in that y value. Right, again, what does that mean? Well, this, negative 2, is the slope at this exact point on this curve. So try to do part B by yourself. Same thing. Find the slope, the equation for the slope, the derivative, and then plug in your x value. right? So I multiplied by half, I subtracted 1, I rewrote it without a negative exponent, and I can plug in 9. Usually, I might have wrote y's here. This is where function notation is kind of nice, because if I had written function notation, it would have made a little more sense what this 1/3 is. So look at it in function notation. Right, this function notation, it makes a little more sense to, instead of having a random 1/3, well, f prime at 9 equals 1/3. The slope of, on this curve at 9 equals 1/3, rather than just, a random 1/3 floating. We kind of have this connection to say, well, what was that 1/3? Well, at 9, maybe 9's over here, the slope of that tangent line that just hits that one point is very shallow. It's like 1/3. The last thing I want to, well, I think we've done enough of these. It's the same exact thing. Let's try a new type of question. The last thing I want to look at is find the equation of a tangent line. So it says the line tangent to a curve at a point on the curve is defined to be the line passing through the point and having a slope equal to the slope of the curve at that point. Kind of a mouthful, but if we have our, I graphed our curve over here for x to the third, and they're saying, hey, find an equation of the line that's tangent to that curve at this point, -1, -1. So maybe -1, -1 is approximately here. So if I try to draw a tangent line, so the point itself might be, say, here. And if we tried to make the line tangent to the curve at that point, in the past questions, we just found the slope at that point, right? We found the slope here is 1/3. We found the slope here is about -2. Now it's really just asking you to do one more step. Not only find the slope at that point, but tell me, hey, what's the whole equation of that tangent line? So start off the same way. First of all, find the slope. All right, there's the equation for my slope at any point on this original curve. Well, now we're interested at this point, -1, -1. So let's plug in -1 to see the slope there. So my slope at -1 is 3. We stopped here in the last questions, but now it's really just one more step. Well, we know what the slope is. We'll write the equation of the line. The easiest line to write is point-slope form, because we can just put in our point and call it a day. Right? If it doesn't specify what form of a line it wants, point slope's usually the easiest. Y minus, plug in your y value, equals the slope. We said the slope was 3 there. X minus the x value, well, x minus the -1, and you're done. If, it said slope intercept fine, you could go and distribute and then bring the 1 over, but that's more than enough. See if you could do at least B. Try B. C is the same exact thing, but try that, pause the video, and see if you get the same question or same answer. right? If we take our derivative, we multiply by a half, we subtract 1, I simplified it and put it in the denominator, and now plug in the 9. Well, if I plug in the 9, the square root of 9 is 3. 2 times 3 is a 6. And lastly, put it in point slope. Well, y minus the y value, in this question they didn't explicitly tell me the y value, right? They told me what x is. Well, to get the y, just plug in 9. Square root of 9 is 3. So y minus 3 equals, again, the slope times x minus the x value. And you're done. All right, for homework, I'd like you to try these questions. Again, the answers are always in the back of your book. And so we'll have a short quiz. Oops, this is wrong, sorry. Short quiz on Thursday. And we'll be using mostly the limit definition because I don't want you to forget this work. And then also we'll use a few, and I'll be very explicit to say use the limit definition or use a shortcut. And also, if you want extra practice with your negative exponents, with the power rule, I'll post some extra practice with answers under today's date. All right, so I shall see you tomorrow.